Yeah, welcome to our podcast, FRAIA podcast, and today we have Gianluca. He will present himself shortly here after it, and just to give a little introduction about what we actually try here, we try to go a little more deep and take the more nerdy stuff in this video here, in this podcast, and it is actually to understand how complicated it actually is to work with this kind of AI technology we do. And can you just make a short introduction about yourself?
Of course. I am Gianluca Grimaldi. I am currently the AI development lead at FRAIA. And that means that my day-to-day work involves customizing AI models, building software infrastructure around these models to use them for practical user applications. And in general, I guess my role is to try to think about everything involved in turning these AI features into useful functionalities for the end user.
Yeah, and you're also PhD, and I think it was actually important approach for us because we need a lot of basic research here.
Yeah, I think that's a fair point. I mean, my background comes from academia. I've worked as a postdoctoral researcher for a couple of years in physics. Mm-hmm. And during the last part of my research experience, I started to develop a passion for using artificial intelligence for facilitating the life of a researcher. Yeah. That can mean experimenting with how you can write scientific papers using artificial intelligence tools. How you can create beautiful data visualizations using AI. So I sort of started experimenting with the user side of the AI world. And eventually that led me to start to learn more about how to develop new AI solution, how to leverage the machine learning techniques in order to make AI solutions that would be customizable and tailored to specific applications. Yeah. And I think that this is where I find FRAIA's approach, our current approach, very interesting because we are taking the amazing tools that are available out there, these sort of monuments of human technologies that are the large GPT models, the Claude models from Anthropic, taking these giants of AI and building useful solutions around them. So really bringing this huge potential to the life of real people.
Yeah. And what I actually think is maybe funny here, because when I hear research and university, often I think we are far away from something that can go to the market with. But here we actually talk about research where we can go straight to the market with the research.
It's really applied research at its core. It's just using a systematic approach of experimenting really with the tool we have in order to find what they are good at, how they can go wrong, and how we can prevent them from going wrong.
Yeah. But let's go into it. Conversational AI, what you find so fascinating about that?
I think what's really fascinating about conversational AI is the way that it lowers the entry barrier to powerful computation. Okay. And by that I mean the fact that so far, when we have interacted with the raw power of computers to perform computational work, our way to interact with them has been always very structured. You need to write computer code in order to get a computer to perform your actions. Otherwise, if you make a mistake in this very structured way of communicating with computers, they are not going to understand what you mean. Mm-hmm. This has been why the whole role of a computer developer involves working with code. So it's a very specialized way of talking with the systems, and it means that there is an entry barrier for who can interact with them. Yeah. And this is where conversational AI has huge potential to democratize the access to computational resources. If you're able to explain what you want to an AI system instead of having to follow rigid conventions on how to communicate with it, suddenly, as long as you understand what the AI system can do and cannot do, you are able to use it for your own applications, to make your own idea come to reality. Of course, this is simplifying the interaction with the AI tool, but really the dream is to be able to make it possible for computers to listen to human, to really listen and understand humans. And this, I think, has huge potential applications.
Actually, I'll make a little with Morten. We were talking about can we ever get rid of databases? Because I keep saying that must be the greatest thing to get rid of, to get databases out of it. Do you think this is actually, now we don't talk about in short term because we go deeper into what is so challenged, but when we just look on a broader view?
Right. I guess that my feeling is that in one way or another, we are going to have databases down the line, but what's going to change a lot is the way that we interact with them. So I think that once again, it follows a pattern of removing some of the structuring around the way that we interact with them and being able to express more what we want from the database rather than having to be very declarative about what we want from the database. So I think it's gonna make more flexible the way that we approach them, rather than completely cancel the whole database.
Just put it all in and hope you get it out structured. It is basically
exactly. Yeah. And so from that point of view, I think we are developing new ways to interact with database also in our AI development approach, because the ability to store information is obviously an important part of a conversational AI system. Again, if we try to look at these systems as a sort of attempt to replicate human brain functionalities, some of the things that we do as humans come from the fact that we are able to store information. And I think that in one way or another, database concepts are necessary to implement these features.
Okay.
I think, in a way, the idea that we are making the world of computers more accessible to humans is one of the sides of the coin of why conversational AI can be disruptive. The other side of it comes from the fact that now for computers it's easier to listen to humans. And that opens slightly different applications. For example, it is now possible for computers to go through a very large amount of human written text that is unstructured, it doesn't follow coding rules, but it still contains information. And so far, the unstructured nature of natural language has prevented to extract in a computational way that information efficiently. Natural language processing, and in particular, the latest advancement in that field, which is the use of large language model to interact with human text, that really brings about the possibility to efficiently extract quantifiable information from a huge amount of natural language input. And that can be key. For example, the application can range from being able to go through huge databases of medical records and try to extract patterns from these records. That is something that would have taken a lot of ad hoc natural language processing scripts that go into very high complexity to do that. And now with large language model, the barrier to accessing that information is a lot lower. It's possible to use the LLM semantic understanding of the way that humans speak in order to get to the raw data that are behind that text.
And so what technique do you use to store the data today when we talk about this large language model?
There are a couple of techniques to try to ground large language models into local information. By local information, I mean all of the information that is not present in the training set of large language models. Essentially, these big computational models are ways to interact with this huge database of information that they have been trained to work with. Yeah. So everything that is outside this database does not exist for them. Yeah. The most common way to currently try to give them extra information in a way that keeps them very grounded and very focused on the information, it's called RAG. This approach stands for Retrieval Augmented Generation. And it can be, simply put, it just describes the process in which information is stored in a database with numbers associated with each small segment of text, so that those numbers are related with the semantic content of the text. Now, that is a bit of an abstract way of talking about this, but essentially what it means is that you can take any chunk of text, create numbers based on the text, and compare how close in meaning that chunk of text is to another chunk of text.
Yes, and so how many levels do we talk about here? Because semantic and one number, do we talk about 10, 100, 10,000, millions, parameters when we talk about?
We are talking about, usually in the order of thousands of dimensions for these numbers. So 1,000 numbers associated with each chunk of text, and each one of these numbers is essentially describing some semantic property of the text, some character of the meaning of the text. So once you have this numerical representation of what the text means, it's fairly easy mathematically to calculate what is the distance between one segment of text and another segment of text. And this is actually quite useful because you can store information, any information, into this numerical form. Then when the user is asking their question, you turn that question into a number, into this sequence of numbers, and you go into the database and look for sequences that are similar to the question sequence.
Yeah, so the closest vector.
The closest vector, which is going to be the chunk of text that is closest in meaning to the user question. So this way, you're able to extract the chunk of text from your knowledge base, from your database of information, that are most closely related with the question asked by the user.
It is so out of box. You just put it in, you put it in the vector, and so everything works fine, or what?
Of course, there has been a lot of work done by the machine learning community to develop a proper approach to turn a text into this sequence of numbers. So in a way, we are standing on the shoulder of giants. But yes, at the moment, there are many models available open source, so freely online, that can be taken and freely used to convert text into its numerical representation that can be used for semantic classification. Yeah. So in a way, yes, it can be these models can be taken out of the box and used to have to create order in their semantic classification.
And it doesn't matter what language you put it in and what language you take it out when we talk about the semantic. So, for example, what we talk about, if we put that into one piece of chunk, we put into a vector database and we speak English and you ask it out, will it still be the same vector we are talking about?
As with most of these machine learning tools, their performance depends on what they have seen in the training stage.
Yeah.
So tools that have been, models that have been specifically trained with multi-language input, so text from many different languages, they are aware of many different languages. There can be models that are just specific to a certain language, and then they need to have the right language input in order to be able to understand what is the semantic meaning. But there are definitely models out there that have understanding of many, many different languages, and therefore allow to flexibly understand the semantic meaning of the text, no matter what its input language is.
And what do you see some of the biggest challenges when we talk about a RAG system? So yeah, where's the blind spot? Where's the biggest headache here when we talk about the RAG?
Right. I think the RAG concept is very powerful because it's fairly simple at its core. It's just about retrieving information that is related to the question that a user asks, and then feeding that information into a large language model that is asked to synthesize that information into an answer. Yeah. So as long as the retrieval of information works well, and as long as the LLM has enough logical understanding of the input so that it can use it to properly answer the question, then the process works. But each one of these steps has its own issues. First of all, retrieval of information from the database might or might not work. This depends on a lot of parameters that can be used in a RAG system. You can change how many vectors are you going to retrieve from the database based on the user question. If you decide to retrieve only 3 vectors, you are sending a small amount of information to the LLM, but potentially you need to take input from 5 points of your knowledge base in order to be able to answer that particular question. So in that case, you don't have enough. You're missing some of the context necessary to answer the question. There are questions that might need to know something about all of the database in order to be effective. And that's where the RAG approach starts to show its weaknesses. It's not possible to retrieve all of the knowledge base and send it all to a language model for it to work on, because the language models have a fixed, it's called a context window. It's the amount of text that they can get in and still be able to produce an answer on it. So given this constraint, you have to be selective on how much you retrieve from a RAG database in order to be able to produce an answer on top of it.
Yeah, and so we've also seen, for example, if you have a long context window, it will remember better what you said in the beginning. It's like a curve. It will be less good what is in the middle, and it will be better in the end again.
Absolutely, yeah. And so what you are touching on is the concept of having to understand how to pass information to LLMs in order for them to properly handle that information. And this is something that originates from the fact that we don't really understand how LLM models work. This is something that is kind of interesting of this new technology. It's probably one of the few examples of technology that we have developed as human beings in the last couple of hundred of years, where we can develop the technology, but we don't entirely understand why it is behaving the way it is.
Yeah.
So even the same companies that develop the largest language models, they know how to set them up, but they don't understand how the parameters of the model individually, how they are affecting the output. And this is something that has major consequences, because it means that we are going more or less by trial and error in exploring what is the relationship between the input that we give these models and their output. So for example, what you mentioned just now, the fact that if you give information at the beginning of a prompt, that is represented in a different way from the information that is given at the middle of the prompt. This is a sort of emergent behavior that people have noticed, but it was not designed this way in the LLM.
It's something copy the human behavior actually, because it's actually how human. What is in the beginning of a talk you remember better than what is in the middle, go away somehow, and what is in we actually remember better the human behavior actually.
Exactly, it does. It ends up having similarities with human behavior, and it's a complex result of a combination of the structure of the data that the models are trained on and their architecture. So exactly what logical components are being activated inside the model when information goes through it. So at the end, it ends up being largely a black box in the way that sometimes this model behave. And this means that it requires a huge amount of trial and error in order to understand how the systems are going to behave in different situations. And this, I think, is something where a lot of improvement can be done. How do we deal with the fact that we are just constrained to anecdotically try different inputs, different parameters, different prompts, and check how they impact the behavior of an LLM system?
Can you try to explain, for example, if we have a soccer team, for example, and we ask, for example, about who's the tallest player, and actually explain why it's so complicated actually to answer when we talk about the RAG, but actually what can we actually do about it?
Right. I think that is an example that we have. It's sort of one of the simplest examples to showcase what are the limitations of RAG. You can easily put a lot of information about well, anything you want, but in this case, you can put information about a soccer team inside a RAG database. So you can have the names of the players stored in vectors, and you can have vectors that contain the name of the player and their height, right? So it should be a fairly easy retrieval task to ask a RAG chatbot for what is the height of a certain player, and the chatbot will easily get back the correct answer. What it does is that it goes into the database, looks for segments that contain information about that player and are talking about height, and then it's able to rephrase that information and present it to you as an answer. So that works well.
Yeah.
But then if you try to ask a slightly different question, which is, who is the tallest of a particular team?
Yes.
So already the situation becomes quickly more difficult for the RAG system, because it can retrieve a certain number of vectors from the database, a number that you have specified beforehand. And now if this number is less than 11, well, actually most teams are going to have more than 11 players, but let's say that it has less than 11, then is not going to be able to find enough vectors in the database to have the height information of all of the players in the team.
Yes.
And therefore is going to return, likely, a wrong answer. It's an obvious way in which a RAG system can go wrong, but it's actually a pretty general thing. You can generalize this sort of behavior as when you ask about a particular fact, about one particular entry in the database, you can think about it as a factual request. You're asking for one bit of information about something. And this is something that the RAG systems can do pretty well, if that bit of information is self-contained within one single segment of text. But suddenly, if you're asking about something that requires a more holistic comprehension of a larger body of text, immediately these systems start to struggle. So this is the description of sort of like fleshing out the problem. Fortunately, this sort of approach is pretty flexible and allows to start implementing strategies to compensate for these errors. First of all, it is possible to try to be flexible in understanding how factual and how holistic a question is. And if you're able to pre-classify the sentences, the questions, you can actually dynamically change how many vectors you're retrieving from the database in order to accommodate for something that needs more context or less context. Mm-hmm. At the same time, you can come up with strategies to have LLMs produce a plan of actions that need to be taken in order to retrieve all of the information necessary. Mm-hmm. For example, if you have a RAG system that needs to retrieve all of the heights of the players in a team, what you can do is that you can have an AI model come up with a list of actions, which in this case would be find all of the names of the players, mm-hmm. and then for each name, find the height of player X. Yes. So suddenly, the whole complex problem is split up in simpler operations that are factual in nature, mm-hmm. and that can therefore be completed successfully by the system. So what I just described are two different ways in which you can start enhancing RAG behavior in order to complete more complex tasks. Yep. And I think this is a pretty general approach. You can come up with more and more complex RAG schemes to solve more and more complex tasks. It also starts showing what is the problem with trying to build this complex RAG solution. The problem is that your solution depends on the quality of your solution depends on the task you have. No two approaches will be. No two different applications will have exactly the same approach, mm-hmm. to solve them. And at the same time, it starts showing that if you want to tweak one of these complex RAG approaches to a particular solution, so you have a huge amount of parameters that you can change. We talked about vector numbers, but you can have difference in the structure of the segments stored in each vector. You can have differences in how much pre-processing of the data you are going to perform, what are the parameters of the LLM that is going to summarize this data to produce an answer. Mm-hmm. So once you start taking in all of the amount of different combinations that can be used to set up these RAG systems, you start realizing that going by trial and error experimentation is gonna explore a very small portion of the whole parameter space available for RAG solutions. And this is something that it's very important for us, mm-hmm. to become better at having approaches to fully explore the parameter space.
Yes. Yeah, because it sounds like you're almost infinity possibilities when you take every component you actually can turn on. And so actually, how do we actually how do we approach this challenge in FRAIA?
Right. I think the key to approaching these challenges is to have good ways to evaluate the output of the RAG system for our particular target goal. Mm-hmm. And that essentially means being able to build automated evaluators.
Okay.
An automated evaluator, it's a system that should have the property of being able to look at the knowledge base. So look at the vector database with all of the information it has in. Look at the questions that have been sent to the RAG system, and look at the answers that the RAG system produce. Mm-hmm. And then give a rating for how well did the RAG system answer the questions. Mm-hmm. And how well the sort of quality of the answer is going to depend on the task. There are going to be RAG applications in which you are only concerned about accuracy of the answer. Mm-hmm. There are going to be applications in which you're interested about a combination of accuracy and the cost it takes to run the whole system.
And who decides the rank? It is an AI, it's a human, who decides the rank of an answer?
Right, so the idea is that you could have a human potentially rate the answers, The only problem is that it's an approach that does not scale. The moment that you want to get a feeling for how the RAG system is working on a variety of different applications, you need more and more people, humans, to have a look at it. And the moment that you start having more and more questions, you completely lose the possibility to have a team of people handling this task. So it's really paramount to develop automated AI approaches to look at the output of this AI system and give a rating to it. So it's a concept that has emerged fairly recently in the LLM field, the one of using large language models as judges for other large language models.
And how good are the judges?
They are surprisingly good, and we can come up with explanation for why they are. Once again, at the bottom line, it all comes back to this black boxy nature of large language models. Somehow they end up being surprisingly good judges of their own output. But this is something that is extremely useful because it allows to use a certain complexity of a large language model. For example, pick one of the large language models with 70 billion parameters. Use it to answer certain questions based on a RAG architecture. And then if you ask the same model to give a rating for the quality of that answer, the rating is going to be, if the model is large enough, the rating is going to be very close to human rating. And that is actually, it has often been proved, it has been proved that this rating is often more aligned with the average human rating than the average alignment between two different human raters. So it's really hitting at the ceiling of how much agreement you would have in any case if you had more than one person rating a database of question and answers. And this is really something crucial because it means that we can start using these AI models to automatically rate chatbot output and therefore really handle an amount of question and answers and an amount of different applications that would be totally unfeasible with only human rating. And this is something that we are putting a lot of effort and interest in because we think that it's the key for a couple of crucial steps that need to be fixed in order to start having RAG applications that really deliver value for clients. The first point is find the optimal way to use a RAG solution for a particular application. So as I said, there are many, many different parameters that can be changed. So if we don't have an automatic way to explore the space of possibilities that this parameter offer, we are never going to find the best possible use of the current architecture of these RAG chatbots.
Yeah, so when you have evaluators, how will you actually use that kind of information to optimize it?
Right, the idea is that once you have the evaluator, you have a metric. You have a number that you can associate with each configuration of the chatbot. And that number is going to tell you how well your chatbot is performing the task that it was designed to do. So once you have that global number, you can go back to the drawing board and say, we tweak one of the parameters of the model. How does that change the evaluation number? So now you get two different numbers. And you can continue updating the parameters of the model in an automated way. So there are many different algorithms that can be used to explore the different combination of parameters. All of them end up producing an overview of how much your metric changes as a function of the parameters. And eventually, these algorithms end up finding the combination of parameters that make the metrics closer to your desired value. And that is done entirely without the help of human input. So you can really have a cycle where you initialize a certain ranges for the input parameter that you think are likely to be useful, and then leave the system be, leave it operate and find its optimum.
Yes.
And what you have at the end is a set of parameters that will give you the best possible configuration for the chatbot.
Yeah, it sounds quite interesting. It also sounds like the cost. If we talk about the cost, like you say, there are almost infinity options about how when you can adjust everything, and if you have to run a loop, evaluated by AI, it can be an infinity loop almost. But it is actually, when you talk about the optimization, is to get to the maximum level optimized point as fast as possible, because every loop costs some money.
Exactly. Yeah. And I think it's going to be something that we are very interested in, is to get better and better at understanding how efficient we can be in that process, so that we can give the full potential of using these optimizer loops for the client. So if we figure out that for a certain application, computationally speaking, it's running a whole optimization loop is very expensive, then it becomes something that we can provide on a case-to-case basis. We can basically tell to the client, you are going to be able to optimize. If you want, we can optimize this model for you. We can run this optimizer. It can provide you with the best possible configuration for the chatbot as a sort of a one-off optimization. But in solutions, in situations where the computational cost of this optimization loop is not so high, suddenly you can start implementing more advanced features, like having the optimization loop run every single time new information is updated in the database. Potentially having the optimization loop run periodically in time to check if the quality of the answer it's still the same it was a couple of months ago. It might change because the fundamental LLM on which the RAG model is based on might have changed. This sometimes is the case when you use proprietary LLMs. The pattern of questions that are asked to the chatbot might also change in time. So being able to have a flexible optimization loop could allow us to really monitor in real time what the output of the chatbot is, and in real time find the best possible combination of parameters for the evolving situation.
Okay, and when we actually also talk about prompt optimization or in contextual learning, the other one is optimization of the entire RAG system, as far as I understand it. And so we only have where you actually only try to optimize. For example, when you go to ChatGPT today and you ask one question, it cannot come out with the answer. You can rephrase how you ask, and so it can answer. I guess the same with the RAG. When you ask some question, if you ask it in one way, it will not understand what you are talking about, and you ask it in another way, it will actually understand what you are talking about. Absolutely.
I think I spoke fairly in a fairly general sense about parameters of a RAG system. What you just mentioned, prompt optimization, can be thought about as one of the parameters of a RAG system.
Okay. Yeah.
So you can think about having a set of different prompt strategies that you can use to feed the information to the LLM. And as you said, if you have a way to try all of these prompting strategies one by one and see which one gives the best metric for the quality of the model output, then suddenly you have a way to take the trial and error out of the prompt engineering.
Yeah.
And really like leverage the understanding that the metric has of the output product, rather than relying on a subjective human perception of what the of what the quality of the output is.
Can you try to put some few words on it? Why the RAG is so important? Can we not just take the LLM and fine tune it, train it by ourselves, whatever, and so we forget everything about the RAG?
Right. I think so. What just to put it in context, you're referring to the idea that instead of trying to provide a database of information to an LLM model, you can change the parameters, internal parameters of the LLM model, to teach new information to the LLM model itself.
Yeah.
So that would basically, the idea would be that once you have retrained the model on your own database of information, which is called fine-tuning, then you can ask directly to the LLM model questions about your local information, and it will be able to answer.
Yeah.
So the question would be, why would you use a RAG approach to feed the information to the LLM when you can just teach directly to the LLM the new information?
Yeah.
And the reason is that in the RAG approach, you are able to stay a little bit closer to the initial data that you put in, while using the data to train an LLM runs into the issue that I mentioned earlier, which is the fact that LLMs are still a little bit of a black box. So you don't know exactly how your information is processed inside of the LLM. You don't know exactly for a given set of input how your input will extract your local information from the internal knowledge of the LLM. And this practically means that fine-tuning is a little bit more susceptible to hallucination than RAG is. And by hallucination in the LLM context, we mean when a large language model starts making up information that is not correct, that was not present in its input data, or anyway is not related to the question asked by the user. All LLM models have the tendency to have hallucination. It's a byproduct of the way that they work. The advantage with RAG is that if you instruct an LLM to specifically answer just with the information contained in the database, as long as the information contained in the database is correct or relevant, then the LLM is more constrained to follow that information. While instead with fine-tuning, you're more susceptible with the LLM internal workings sort of getting sidetracked towards information that is not relevant to the question.
Okay, sounds interesting. Any other last words here before we round it up?
Yeah, I think my personal take on sort of the path we are on with FRAIA, and in general the current status of AI development, is that we are all waiting for where this technology can bring us. We are all waiting for the next big jump in technology. But at the same time, I think that so much can be done with the current version of the AI model that are available, with the current large open source models we have, with the GPT models from OpenAI and every other like big actor in the LLM field. These models are already so good at understanding at least the semantic of human language that they can open a myriad of different applications that we have really not been able to tackle so far. And this really does not require a big artificial general intelligence jump in order to start producing real effects on society and on the life of customers and people really in general.
And it also looked like the next model where hallucination at the same level.
Right.
We just have more feature. Now it can listen, now it can see, now it can hear, now it can put a picture out. But the main stuff we are trying to fixing in FRAIA about we can actually put some information in and get the factual correct information out in the other end. It look like it is not what we are focusing on when you look at the main field out there.
Yeah, definitely. Like if you are able to really make use of all this functionality that is already out there, you can really produce incredible new tools and new software solution. And I think that's what really makes it exciting to work on these topics right now.
Yeah. But thanks, actually. I hope you don't fall in sleep out there.